All right, hey everybody. I hope this video finds you doing well. Wanted to quickly review the central limit theorem with you and then work out another example. Highly encourage you, go to your notes. We did lots of details and lots of examples there, but I thought maybe having one on YouTube that you could watch might be helpful to some of you. So here we go. So let's just remind ourselves what the central limit theorem is saying. So what's our setup? First and foremost, we start with a data set, which we're going to think of as representing a population. So this may not even be a data set that you can explicitly write down. Maybe it's like the ages of every U.S. citizen or something like that. Possibly too big to write down, that's fine. Start with a data set. We do need to know its mean mu. We'll say mu sub x equals its mean, and sigma sub x is going to be its standard deviation, right, of course. And so then we're going to consider all samples of size n. So you just take a bunch of samples from your data, fix n. I don't care what n is. Typically we want it to be 30 roughly or more. Consider all samples of size n. And we talked about in class how you can look at the average, right? The average of each sample. So this is the average of each sample, and of course of size n. And as you pick a sample, its average changes. And so we talked about how when you start with a population distribution, you get these sampling distributions. You get a new data set for the mean. And the idea is, again, each sample gives you a slightly different average depending on the values. And then we can also talk about sigma x. This is just the sum of each sample. And so from your data set, as you pick samples, you can build these new random variables, and these have distributions of their own. So our original data set might have a distribution that is majorly non-normal. It could be majorly right skewed or left skewed. Who knows what it looks like? But we learned that these distributions are always going to be normal. They're always going to be well behaved. And so I want to remind you what that says, what the central limit theorem says. It says that the sampling distribution for x bar is normal. It's approximately normal, with the mean is the same as the original mean, and the standard deviation is the population standard deviation divided by the square root of your sample size. Think about what this is saying. It's saying as you let your sample size get bigger and bigger and bigger, as n gets bigger, the square root gets bigger, and as the bottom of a fraction gets bigger, the whole fraction gets smaller. And so what it's saying is the larger your samples are, the less the standard deviation is. They're going to get more and more accurate when it comes to estimating the mean. So that's the first one. And the second thing that we learned was that sigma x is also normally distributed, but the mean and the standard deviation change. The mean is n times the original mean, and then the standard deviation for sigma x is root n times the original standard deviation. And so here this is saying the larger your samples go, then the larger the standard deviation is going to be, because when you're summing, all these numbers are just getting bigger and bigger and bigger. So that's the central limit theorem in a nutshell. Again, please see your notes. If you want to see examples of actually writing down what do these sampling distributions look like, we did that, and I would highly encourage you to check those out. I'll end this video here. In the next video, we'll do a quick example.